So 1084 and 15 and 20 are by far the most popular combination of steels to use in Damascus today. But why is it the most popular? How did it become the most popular? And is it the best choice? Are there other choices which may be better? Can you get more edge retention or better toughness? What happens if you combine different steels together instead of 1084 and 15 and 20? What are the things you need to watch out for, and how can you process them differently to make them more compatible with each other? Are there any steels you really should avoid or need to treat completely differently than 1084 and 15 and 20 to make them work in Damascus? Well, I will answer all of those questions. You just got to watch the rest of the video. Let's do it. In 1973, Bill Moran repopularized Damascus, and he made Damascus from 01 and mild steel. Damascus bladesmiths in the 1970s, 1980s, even into the 1990s believed that you needed a large carbon difference between the two steels. They thought that would give an improvement in performance, and that also gave the contrast you needed between the materials after you etched it. In 1998, Dr. John Verhoeven and bladesmith Howard Clark published a study on pattern-welded Damascus, where they found that carbon would diffuse evenly between the two steels. So even if you had a high carbon and a low carbon, you would end up with roughly the same carbon content throughout, with normal layer counts and layer thicknesses. Carbon is a very small element, so it is interstitial, meaning it sits between the iron atoms, so it can diffuse very fast. Larger elements like manganese, chromium, nickel are substitutional elements, so they replace iron atoms, and thus diffusion is much slower. So the contrast actually comes from differences between the substitutional atoms, not interstitial atoms like carbon. Even before the study by Verhoeven and Clark, Damascus smiths had already been moving on to other combinations apart from 01 and mild steel. So instead of mild steel, you can use a high nickel, low carbon steel called A203E, and it became the most popular choice for the bright layer in Damascus. So this recommendation of using A203E was made in 1977 by what's called the Damascus Steel Research Team of Darrell Meyer, Jim Wallace, and Robert Griffith. They also recommended other things like pure nickel as the bright layer. Anciently, bladesmiths would use nickel steel in some pattern-welded Damascus blades. They would get the nickel iron from metallic meteorites, which typically have 5 to 10% nickel. Oh, in the 70s and 80s, choices for the dark layer would be things like W1, W2, and 1095, basically simple high-carbon steels. And some low-alloy high-carbon tool steels like O1 and O2 were also used. A203E has only about 0.1% carbon. So bladesmiths more and more wanted to use two high-carbon steels. So one of the earliest I found was Tim Zawada around 1990-1991 began using O2 and L6, so two high-carbon steels, O2 having high manganese and L6 having high nickel for contrast. And it became more and more common for bladesmiths to use high nickel steels like 15 and 20 or bandsaw blades. At the time, it was very common for people to call the bandsaw blades L6, despite the fact that L6 has not been used in bandsaw blades as far as I can find. But L6 is similar to many bandsaw blade steels because it has 1.5% nickel. But there are differences I have found between the composition of these steels. So when did 1084 and 15 and 20 become so common? Well, even by 1994, so that's when Jim Rasulis' book, The Pattern-Welded Blade, came out, he did not even mention 15 and 20. And his book mostly talked about combining high-carbon and low-carbon steels. So 1084, 15, and 20 was not popular at that point of its publication. From what I have found, 1084 and 15 and 20 became popularized in part by the Montana Mafia, which is made up of Damascus smiths like Rick Dunkerley and Shane Taylor. Dunkerley said that he began using the mix in 1995 from a suggestion from my father, Devin Thomas. I asked my father why he suggested those steels. He said a lot of bladesmiths would go to him asking for help with forge welding and etching issues, and a lot of people were using difficult steel combinations. And he thought that 1084 and 15 and 20 would be easy to forge weld and would give good contrast and would be easier for these bladesmiths to use. Now, another question I had is why 1084 and not 1075, because 15 and 20 has 0.75% carbon like 1075. So why wasn't 1075 the choice? Why was it 1084? Well, he told me that at the time 1075 was available in wide sheets, so you would have to shear it down to narrow pieces for the billet. 1084 was available as narrower bars, so you could easily stack up the pieces just after bandsaw cutting up the bar to stack with the 15 and 20. So, and for some knife makers, it actually was appealing that the 1084 had more carbon than 1075. So they thought the higher carbon would mean better performance or better hardness or whatever. But in either case, 1075, 1080, 1084, those are all roughly equivalent to use along with 15 and 20. And the 1084, 15 and 20 combination, even though it was popularized relatively recently in the late 1990s, it's basically ubiquitous now. If you find the study of the history of knife making and Damascus making interesting, like this little historical story I gave right here, you might want to read my book, The Story of Knife Steel. I have 1,000 different stories just like this one about different knife makers who use different knife steels in different ways and popularize different things about the history of different knife makers and knife companies, and also the history of the different metallurgists who developed the knife steels that we use today. So if you want to learn more, go read The Story of Knife Steel. Now I'm going to discuss the different elements and what effects they have on contrast and etching, but there are a few notes to give or caveats to provide first. One is that different etchants may lead to different levels of contrast. Ferric chloride is the most common, but you can also use things like sulfuric acid or hydrochloric acid, and it's becoming more and more popular to use a coffee etch, usually after a ferric chloride etch. But all of those different etchants can lead to different levels of contrast. Another thing to mention is that your etching and polishing technique can affect the contrast. So how much are the bladesmiths polishing the steel before the etch, and how are they polishing it after each segment of etching? Because often you do it multiple times. So that technique that they are using can affect the contrast. Another is that photography has a big effect on contrast. So you may have experienced times when you saw a picture of a Damascus knife and the contrast was very apparent, and then when you saw it in person, you saw that the contrast was much more subtle and that you might have to move the blade in the light to see the contrast more clearly. So despite all of these difficulties, I'm going to try to make some generalizations about effects of different steel elements on the level of contrast after etching. So if you disagree with my assessment, please feel free to say so in the comments. So as I mentioned in the history of our steel choices, nickel has long been understood to lead to a better bright layer. And that's why 15 and 20 with its 2% nickel has gotten so popular. Now, one thing that we should discuss briefly is that in the past, we've often thought about the nickel itself leading to resisting etching. But if you etch 1084 and 15 and 20 separately, you'll see that both of them darken just fine in acid. So I think the effect is a little bit more complicated. I think it's more of an anode-cathode effect where the 1084 is being etched preferentially rather than the 15 and 20 itself resisting the etching. It's that the 1084 is more susceptible to etching because the 15 and 20 is the more noble of the two metals. Now, I haven't seen any studies to confirm this, but it seems like something that must be going on to me. So if anyone knows of any good research in this area, please let me know. So there are other steels with high nickel which are used. So some rarer steels have 4% nickel, such as 4800 steel powder or Bowler K600, that's also called 1.2767 steel. L6 has a little bit lower nickel at 1.5%, and 8670 gets some use and it has only 0.9% nickel. Generally, the more nickel is in the steel, the brighter it is after etching. Unfortunately, there aren't any low alloy nickel steels with any significant vanadium or tungsten additions, so there isn't much wear resistance in any of these nickel steels. So you have to get your wear resistance from the other steel in the Damascus combination usually, if you want a high wear resistance combination. Now, another element which is pretty well studied and understood is manganese. So higher manganese leads to darker etching. So in the Verhoeven-Clark study, they found that if they used 1018 steel with 0.75% manganese and 1086 steel with 0.4% manganese, the 1018 was the dark layer, even though it had lower carbon. So in the past, bladesmiths thought that you needed a high carbon dark layer and a low carbon bright layer, but if the manganese contents were different, Verhoeven and Clark actually found the opposite. So manganese is a more important element from this standpoint. So for dark layer steels, we want more manganese. So the higher manganese in 1084 relative to 1095 and 1075 does lead to it being somewhat darker when used in combination with 15 and 20. There are some steels with even higher manganese contents, such as O1 with 1.2% manganese or O2 with 1.6% manganese. The European version of O2 is called 1.2842, and it has 2% manganese, and it etches darker than maybe any other common steel. So usually, the more manganese, the better it works as a dark layer against a nickel steel or some other combination. Now, chromium is a bit more mysterious, and I am having a hard time finding really concrete examples of the effect of chromium. So in the Verhoeven-Clark study, they found that 52100 and L6 had poor contrast, and 52100 has high chromium at 1.5%, but it also has low manganese with only 0.35%. I have seen some knives occasionally that use 52100 and 15 and 20, and the contrast can be okay in some of them. So here is a Bowie knife by Aaron Wilborn, and the contrast looks pretty good. It's mostly gray on gray rather than like a bright layer and a really dark layer. But again, the photography matters, and he may not have been going for a high contrast look between the two, depending on how he was etching and polishing. 1095, however, is usually a little bit darker than 52100. It has slightly more manganese, like 0.4 or 0.45%, and it has 0 chromium. It typically etches darker than the 52100 in combination with 15 and 20, as you can see in this knife by Blake Nichols with Greg Shahan Damascus. O1 still etches quite dark, even though it has 0.5% chromium, and so does 1.2842, even though it has a little bit of chromium. 80 CRV2 is also generally considered sufficiently dark in combination with 15 and 20, even though it has 0.5% chromium and only 0.4% manganese. 5160 has relatively high manganese at 0.85% and also somewhat high chromium at 0.8%, and it also etches pretty dark. So I think overall it looks like low amounts of chromium do not have a large effect, but it might be that higher amounts like the 1.5% at 50-100 may affect how dark the steel etches. Other elements like vanadium and tungsten and molybdenum, as far as I can tell, those elements do not affect etching. But we should mention that high vanadium and or tungsten additions are good for high wear resistance in these low alloy carbon steels that we are discussing. And so because those are the best choices for high edge retention in Damascus, I have a chart here of some of the common ones. So steels like Cruforge V or V Toku or Apex Ultra or 1.2562, all of those steels have vanadium or tungsten additions, and they have significantly higher wear resistance than a steel like 1084. So they're good choices if you want better slicing edge retention. Another thing we should discuss is 3-color Damascus, it is sometimes called, or even more colors potentially. So you can use certain combinations so that you can get multiple shades of gray or white. A common example is to use a dark etching steel like 1084 in combination with 15 and 20 and pure nickel. So 15 and 20 does not resist etching as well as pure nickel does. So you get a really bright layer with the pure nickel, then a light gray layer with the 15 and 20, and then a dark gray layer with something like a 1084. Sometimes there is even an intermediate shade between 15 and 20 and 1084. One example I found was this person used 1.2842, which is the European O2, along with 80 CRV2 and 15 and 20. So the 80 CRV2 was in between how dark the 1.2842 was and how bright the 15 and 20 was. There can also be some contrast between 2% nickel 4600 powder and 4% nickel 4800 powder. So here is a Roadrunner by Cliff Parker, and the eyes are 4800 and the beak is 4600, and you can see a little bit of a color difference between the two. So here we have multiple shades of gray along with the bright nickel sheet that he used in the shape of the Roadrunner. I should also mention that I'm not going to discuss stainless steels, high alloy steels, or Sanmai in this video. It just got too long, and it takes too long to talk about stainless. There's too much to say, so I'm going to do that in a future video. If that's something you are interested in, make sure you subscribe so you know when I release that video. It is very common for Damascus smiths to use very high forge welding temperatures like 2300 or even 2350 degrees Fahrenheit, sometimes even hotter. This typically works for steels like 1084 and 15 and 20 because they are eutectoid steels, around 0.8% carbon. However, the higher the carbon content, the lower the melting temperature. This is why cast iron has really high carbon content, so that the melting temperature is really low so it can easily be cast. The grain boundaries melt first. So after the grain boundaries melt, when you hit the steel with a hammer, it will crumble during forging. This is especially important to keep in mind when steels have higher than 1.2% carbon, like 26C3, White No. 1, Apex Ultra, 1.2562, Blue Super. All of these steels are more likely to crumble during forging and forge welding if you're trying to use those really, really high temperatures that you might be used to using with 1084 and 15 and 20. Even 1% carbon steels like W1 and 52100 can cause problems because they are a little more sensitive, being at higher carbon. So with very high carbon steels, usually you need a little bit lower temperature for forge welding, like 2150 to 2200 degrees, which is around 1175 to 1205 Celsius. A longer soak time can help make up for the reduced forge welding temperatures. In terms of ease in forging, I have a separate article on how difficult it is to forge various steels, and I have a loose ranking of some typical steels in terms of how difficult they are. Typically, higher carbon and higher alloy steels are more difficult to forge. One reason is because they are more likely to have undissolved carbides at the forging temperature. Carbides don't deform as well as steel, and so that increases the difficulty. Steels below the eutectoid, around 0.77% carbon, are very easy to dissolve the carbides. The carbides dissolve at a very low temperature, well below the forge welding temperature. Steels with high carbon, like 26C3, may still have some carbide near the forging temperature. Even 52100, even though it has 1% carbon, also has 1.5% chromium, which also raises the temperature at which carbides dissolve. However, even 26C3 and 52100 will have very little carbide when compared to high alloy steels like D2, and the remaining carbides are much smaller, so usually they're easier to forge than high alloy and stainless steels. Some low alloy steels have vanadium and tungsten additions for greater wear resistance, like CrewForge V and Apex Ultra. Vanadium and tungsten carbides are more likely to be present at forging temperatures. They're very good at pinning grain boundaries, but that also means they can affect ease in forging. In terms of how easy it is to get two steels to forge weld together to diffusion bond in an oxygen atmosphere, oxides form on the surface, which prevents diffusion bonding. What flux does is dissolve the oxides so that the two steels can be in contact with each other and diffusion bond. Some alloying elements will change the type of oxide that forms. The most common is chromium. So like stainless steels are famously very difficult to forge weld because they form tenacious chromium oxides that are not removed with flux. So the more chromium is in the steel, the more difficult it is to forge weld. Manganese and nickel do not seem to have a big effect, which is why 1084 and 15 and 20 are easily forge welded. However, if you're forge welding steel in an oxygen-free environment, virtually any steels can be forge welded together. Now, another potential issue with forging and forge welding is cracking after forging. This is most common with high hardenability steels, so oil hardening and especially air hardening steels, but oil hardening steels like O1, O2, L6, they are more sensitive to cracking after forging. If they quickly air cool, they can partially harden, and when they partially harden, you're more likely to get cracking post-forging. It helps to slow cool below a certain temperature, like 1400 degrees Fahrenheit, 760 Celsius. But slow cooling from very high temperatures can lead to carbides forming on the grain boundaries that are difficult to eliminate. Normalizing typically gets rid of these, but air hardening steels cannot be normalized. After you cool to room temperature, the steel can be cycled or annealed to remove stresses in the material so that cracking doesn't happen. Now we can talk about compatibility for heat treating. Semi-frequently, I get questions from knife enthusiasts and even some Damascus smiths about combining non-typical steels together, sometimes really bizarre combinations like MagnaCut and 15 and 20. Oftentimes, the reason these strange combinations are not compatible is because of the austenitizing or hardening temperature range. 15 and 20 is optimally austenitized from about 1400 to 1475 Fahrenheit, 760 to 800 Celsius, while MagnaCut is austenitized from 1950 to 2200, which is 1065 to 1205 Celsius. As you can see, these two temperature ranges do not overlap. If the MagnaCut was austenitized from 1475, it would be very soft and its corrosion resistance would be much lower than austenitizing at 1950 or above. If the 15 and 20 was austenitized at 1950 or higher, it would have very poor toughness from grain growth. Some steels can be pushed a bit higher or a bit lower than typically recommended in a datasheet so that you can get two steels to work together, but this is not an example where that can happen. A MagnaCut in 15 and 20 would be an extreme example, but there are even some low alloy non-stainless or simple carbon steels which are not as compatible as you might think on first blush. Manganese and nickel push down the temperature at which steel transforms to austenite, and chromium increases the temperature where the steel transforms. I did an experiment to illustrate this using 1084, which is kind of our base condition, with a regular or medium amount of manganese. Then 15 and 20, there is 2% nickel, which reduces the transformation temperature, and chromium for 80 CrV2, so 0.5% chromium addition, raises the temperature at which it transforms. So I took normalized versions of all of these. So I heated them up hot and air-cooled them, and then I did 25-degree increments and quenched. Then I measured the hardness. 15 and 20 was fully austenitized from about 1325 Fahrenheit, or 720 Celsius, while 1084 was still dead soft from that same 1325. Same with 80 CrV2. The 1084, though, was at its maximum hardness roughly from 1350 Fahrenheit, or 732 Celsius, only 25 degrees hotter. The 80 CrV2 with the 0.5% chromium, it needed 1400 degrees, or 760 Celsius, to achieve its full hardness. Now again, this was from a normalized microstructure, not annealed. The annealing procedure can have a big effect on the heat treating behavior. So I have a chart of 80 CrV2 heat treated from 3 different conditions. First, I have the same perlite normalized condition on the left, where you can see it was close to full hardness from only 1400 degrees Fahrenheit. From supplier number 1, it needed about 1525 to 1575 to achieve full hardness. From another supplier, labeled here supplier number 2, we needed over 1600 degrees, something like 1650 Fahrenheit, to get full hardness. And the difference is in how coarse the material is. So the supplier number 1 had a relatively fine spheroidized structure, so round carbides as opposed to perlite in the normalized steel. Supplier number 2 had larger carbides, and you needed more temperature to dissolve. And so when we're combining 2 steels together, they need to have a compatible heat treatment, and they need to have a compatible starting microstructure so that they austenitize within a similar range. Chromium is an important element to pay attention to because it typically shifts up our optimal austenitizing temperature ranges. Chromium steels are usually in the range of something like 1500 to 1550 Fahrenheit, 815 to 845 Celsius, which is higher than a normal steel with only manganese or nickel, which is usually around 1475 Fahrenheit, or 800 Celsius. 15 and 20, since it doesn't have any chromium in it, has less of an effect of the starting microstructure. So I have the normalized condition again, then I have the steel company anneal, and I also have what's labeled as a fast DET. So the fast DET gives a fine spheroidized carbide structure. The steel company anneal is a coarse spheroidized structure, and normalized, of course, is perlite. So with the perlite condition, we were fully austenitized at 1325. With the fast DET, that was pushed up another 50 degrees to 1350. And with the coarse spheroidized structure from the steel company, that was pushed up again to something like 1375 or 1400. Now, this range is much smaller than what we saw in the 80 CrV2. It is less affected by the starting structure because it doesn't have any chromium, but it's still something to pay attention to. The starting structure will affect how it heat treats. Another important factor for choosing an austenitizing temperature is toughness and grain growth. So there is an upper end of acceptable temperature. We were talking about the lower end of the temperature before. Now we're talking about the upper end. So we did a new experiment with 1.2519, that is a tungsten vanadium high carbon steel, 15 and 20, which we have discussed a bunch already, and L6, which has 1.5% nickel, but it also has a chromium addition. So when we look at the hardness of these different steels, the 15 and 20 is basically flat. So we did a 15-minute austenitize, we quenched in Parks 50, and we tempered at 400 degrees. The 15 and 20 hardness was about 61 Rockwell, no matter what temperature we use, 1400 up to 1600 Fahrenheit. The L6 and the 1.2519, they increased in hardness as we increased the austenitizing temperature. All of these were from the steel company annealed microstructure. So with the chromium alloyed steels, you had to austenitize hotter to get a higher hardness, where the 15 and 20 was flat because it's very easy to dissolve everything in that steel because it doesn't have any chromium. When we look at toughness, we also see some interesting trends. In this case, the 1.2519 is flat for toughness. Even though our hardness is increasing across the range, the toughness was flat from 1400 to 1500. So 1500 is the best choice for the balance of hardness and toughness. And then the toughness dropped a little bit at higher temperatures, either because we got a little bit of grain growth or we just got more hardness and more carbon in solution. For L6, we peaked in toughness at 1500. So similar to other chromium alloyed steels. We can dissolve a little bit of carbide and get a little more hardness and more toughness by going up to 1500 degrees Fahrenheit instead of something like 1450. And then the toughness drops from there, presumably from grain growth, since L6 does not have that much carbon in it. 15 and 20 showed a different behavior. The toughness was high when we used 1400 and 1450, and I've also done an experiment from 1475 in the past, which also showed high toughness. But austenitizing at only 1500 degrees led to a huge drop in toughness, which comes from grain growth of the steel. 15 and 20 doesn't have any chromium, and so the carbides dissolve easily, and once the carbides are gone, there's nothing to pin the grain boundaries. Grain growth happens very rapidly. So you have to be careful with these low carbide steels like 15 and 20 and 1084 because they are very easy to overheat and get grain growth and poor toughness. I see a lot of knife makers that have this issue where they keep battling 1084, they keep breaking their steel and seeing really coarse grain because it's really easy to overheat these steels if you're not using a furnace with a controlled temperature. But all of this does affect different steel combinations. So if we're using 80 CRV2 and 15 and 20, a combination which I am seeing becoming more and more common, 80 CRV2 has that chromium addition which pushes up its optimal austenitizing range. But 15 and 20 needs to be austenitized at 1475 Fahrenheit or below to avoid poor toughness. So we get a bit of a mismatch. The 15 and 20 needs to be 1450, 1475. The 80 CRV2 needs to be 1500 to 1525. So in that way, L6 can be a more optimal steel to combine with 80 CRV2. And 15 and 20 is more optimal to be used with steels like 1084. However, we can process the 80 CRV2 so that it can be more compatible with the 15 and 20. Remember earlier when we were talking about the normalized starting structure of 80 CRV2, it austenitizes from a lower temperature. So if we don't anneal the steel, we just normalize it, then it can be austenitized at only 1450 or 1475 to be compatible with the 15 and 20. So what I recommend doing is doing a normalizing step and then a grain refinement step. So normally when we anneal the steel, we would heat the 80 CRV2 to 1400 Fahrenheit, about 760 Celsius, and then slow cool for it to be annealed and soft and have a spheroidized structure. But if we air cool, then it becomes a grain refining step, and it still does become a bit softer. So in my experiments with normalized 80 CRV2, I had about 25 Rockwell, and when I added a grain refining step, it was about 19 Rockwell. So it gets a little bit softer so that it is easier to work, like drill and bandsaw cut, etc. But it also still has that high hardening response, so you can austenitize it lower to be compatible with the 15 and 20. So you can do these kinds of tweaks to your processing to make steels more compatible with each other. Another thing to pay attention to in terms of austenitizing temperature selection is not just grain growth, but also plate martensite. Plate martensite is brittle martensite that forms in steels that have more than 0.6% carbon. 15 and 20 and 1084 with like 0.75 to 0.84% carbon usually don't see this issue, but any steel with over 0.85% carbon, I have seen plate martensite and poor toughness. So 01 and 1095 are two steels that I've seen relatively low toughness, where you'd think they would be more similar to toughness to steels like 1084, which only have a little bit less carbon, but they form some plate martensite and the toughness goes down. In some 01 steel that I found was very sensitive to plate martensite and low toughness, I did different austenitizing temperatures, 1425, 1475, and 1550. All of them had a fine fracture grain size, so the grain size wasn't significantly growing, but the toughness was better with 1475 than 1550, and the toughness got even better using 1425 Fahrenheit. So as we got less carbon in solution, even with a fine grain size, we got higher toughness because we avoided plate martensite. So I'd like to thank my Patreon supporters. As you saw, we did several new experiments for this video that I did, things like the toughness experiments on 15 and 20 and L6 and comparing the different ones and how the different steels austenitize at different ranges. All of that is new experiments, and all that takes time and money, and I'm able to do that thanks to the support of Patreon. So if you would like to support future knife steel research, please join us on our Patreon at patreon.com/knifesteelnerds. You can get articles and videos early there. We discuss things as a Patreon group, and if you become a top tier member, you even get a free Knife Steel Nerds mug. Okay, so after all of that, we should talk a little more about normalizing and annealing. So I thought it best to talk about austenitizing first because normalizing is an austenitizing step. So compensating for normalizing is usually not too difficult with various Damascus combinations. Generally, you take the higher required normalizing temperature. So for example, if you had 26C3, which needs something like 1700 Fahrenheit or 925 Celsius to normalize, and you combine that with 15 and 20, which only needs something like 1550 Fahrenheit or 845 C, you normalize at the higher temperature of 1700. The temperature needs to be sufficiently high to dissolve all the carbides. So 1550 for 15 and 20 would not be high enough for 26C3, so you have to go hotter. For annealing, similar rules apply, though it is a little more complicated. You generally want to use the higher required annealing temperature to ensure that both are annealed. If too much carbide is dissolved in one of the steels, that can mean you end up with pearlite instead of spheroidized carbide, and thus a little higher annealed hardness, but that is usually an acceptable trade-off. As I mentioned when discussing 80CrV2 and 15 and 20, for some combinations, a pearlitic normalized structure may make the steels more compatible. In that case, you would normalize, like normal, at the required temperature for the 80CrV2, which is 1550 to 1650 Fahrenheit. Then you heat to the annealing temperature, and instead of slow cooling, you do an air cool. That's a grain refinement cycle instead of an annealing cycle. Usually, I prefer an annealed steel because you have more control over the final hardness. When you have pearlitic steel, you have maximum hardness or nothing. You have no control over the final hardness. So annealed steel is easier to bandsaw cut and drill, and you also have better control when heat treating. I do have a separate article and video on normalizing and annealing with recommended procedures and temperatures for different steels so that you can line them up and see what the best choice is for normalizing and annealing different Damascus combinations. Steels also have different levels of hardenability, or how fast they need to be quenched to be fully hardened. So there are water hardening steels, oil hardening steels, and air hardening steels. Even within low alloy non-stainless steels, there can be significant differences. For example, L6 is a high hardenability oil hardening steel, while W2 is a very low hardenability water hardening steel. You can use the two together in Damascus, but there is a significant gap between the two steels for hardenability. So to fully harden the W2L6, you would need to quench very rapidly because of the W2 to ensure that both steels hardened. If you used a slow oil, you would likely end up with fully hardened L6 but soft W2. Even 1084 and 15 and 20 have a difference in hardenability because the 2% nickel addition in the 15 and 20 means its hardenability is higher. So I have a loose ranking of hardenability of different steels in a separate article if you want to see how compatible steels might be in terms of hardenability. Tempering leads to darker etching than untempered steel. Some people using Damascus for decorative purposes like jewelry don't think they need high hardness and they'll try to skip the heat treatment, but that leads to poorer contrast. Martensite etches better than ferrite, that's annealed steel, and tempered martensite etches even better than quenched martensite. In terms of compatibility, tempering is usually not that big of a deal. Most steels can be tempered at like 400 Fahrenheit, 200 Celsius, and have good properties. Some steels, though, do have a slightly different range than others. 15 and 20 and 8670 needed to be tempered at least at 350 Fahrenheit in our testing. That's 175 Celsius. While 5160 needed 375 Fahrenheit, the highest minimum needed tempering temperature for good toughness that we have thus far seen. There is also a top end. So there is a phenomena called tempered martensite embrittlement. So here in 15 and 20, when we tempered at 450 instead of 400, there was a drop in toughness. And the temperature at which you start to see TME changes by the steel. Some see it at 450, some see it at 500, and some even higher. So to be safe, 400 degrees is a good choice, 200 Celsius for most steels. And if you're going to use 450 or 500, you need to know that you're not going to see tempered martensite embrittlement. So I already have a whole separate article and video on testing toughness and edge retention of different pattern-welded Damascus combinations, so I'm not going to repeat all of that here, but there are a few key points to mention when it comes to compatibility. Number one is combining a low toughness and high toughness steel generally seems to lead to toughness similar to the low toughness steel. It fractures at the weakest link, and there isn't that much benefit to adding a high toughness steel in terms of overall toughness. Number two, high wear resistant steels with high slicing edge retention generally still cut very well even when combined with a steel with lower wear resistance. So combining Crewforge V in 15 and 20 or Apex Ultra and L6 led to good edge retention similar to Crewforge V or Apex Ultra alone. However, this was due in part to the improvement in edge retention that we saw with ladder patterning. Number three, while ladder patterning benefited edge retention, it also slightly reduced toughness. Number four, a Damascus cutting effect was seen in 1095 nickel Damascus. Most steel combinations do not have hard and soft layers, but using nickel does provide this potential benefit, though there are also potential drawbacks. When you're not attempting to have a Damascus cutting effect, it can be beneficial to have two steels with good wear resistance. For low alloy non-stainless steels, it makes sense to look at steels with significant vanadium or tungsten additions, like Apex Ultra, Crewforge V, 1.2519, etc. However, for low alloy steels, for bright layers, the main choices are 15 and 20 and L6, and neither has much wear resistance. If you're making a Damascus combination for high toughness, you need to have two high toughness steels. So 1084 and 15 and 20 are a decent combination for this. 1084 is somewhat lower in toughness, but the two together still tested at about 34 foot-pounds in a random pattern, as opposed to 45 to 50 pounds for 15 and 20 by itself. So this combination is good for high toughness. So that's a lot to summarize, but it is best to choose steels that have similar temperatures for heat treating. High manganese is best for a dark layer after etching, while high nickel is best for a bright layer. Other alloying elements, especially chromium, can make forge welding more difficult when you're using conventional flux methods. It is important to adjust heat treatment based on the steels that are combined together. And I gave the example of 15 and 20 and ADCR V2, because 15 and 20 sees a large toughness drop when austenitized at 1500, which is around the optimal range for ADCR V2. So if you use a steel like ADCR V2 with 15 and 20, it's best to use a normalized starting structure instead of an annealed starting structure, so that the ADCR V2 can be austenitized from 1475, which is about 800 C. Then it can be used with the 15 and 20 and still have the right combination of hardness and toughness. L6 may be more optimal than 15 and 20 to use along with other chromium alloyed steels, though it does have lower nickel than 15 and 20, so the contrast is not quite as good. It's also a little bit more difficult to work with because of its alloy additions. High carbon steels are more sensitive to overheating because the grain boundaries melt at a lower temperature, which leads to crumbling during forging. High vanadium and high tungsten steels are best for wear resistance combinations, though they typically need to be combined with 15 and 20 or L6, which unfortunately do not have much wear resistance. So, happy Damascus making!